So let R be the region between the curve y equals x squared, that's this line, x equals y squared, that's that line. For the function f of xy equals 9x squared plus 14y minus 23x, which of the following is not a potential location for the absolute max or absolute min? So this is sort of testing the process. And there's 5 locations listed. 4 of them are ones that should be checked, and one of them is one which should not be checked. So, what's the answer? A, B, C, D, or E? Any guesses? This one is more challenging. Now, there are 2 of them which are freebies. What do you always check? Corners. Do we have corners? Yes. There's a corner here where 2 curves come together. Where's that? 0, 0. There's a corner up here where they come together. 1, 1. So you know it's not A or B. Okay. So now that I've ruled 2 of them out, you have a 1 in 3 chance. Yes, that's right. You have a 1 in 3 chance. So the answer is D. Now, I did throw in a bonus fact. There is actually one additional point that you have to check, but that one is not obvious. So how do you run it? Well, we know the corners. Along y equals x squared, we rewrite our function in terms of x. Becomes 23 times x squared minus x. And that's not hard to take a derivative, and we say x equals a half, which gives us our point 1/2, 1/4. Along x equals y squared, it's a hard one. So if you put in x equals y squared, you end up with a quartic, a 4th degree. You take a derivative, you get a 3rd degree. And you might say, how do I solve a 3rd degree? And the answer is you don't. But what do you have? You have points to test. And you say, oh, these are points along the curve x equals y squared. So you don't have to solve it. You just have to check to see if either of them work or not work. And if you plug in a half, you get that this left-hand side is not 0, so it doesn't work. On the other hand, if you plug in a 3rd, it does in fact work. And it turns out that for this particular function, for this particular region, the absolute maximum occur at point C and E. I can't remember which one is which. But that's the answer. All right, good. Well, our thought for today. This comes from John von Neumann, a very smart guy. He said, in mathematics, you don't understand things. You just get used to them. And it was a half a joke when he said it. But I think that there's a little bit of truth here that I want to talk about. Sometimes we have this idea that we're going to have these big epiphanies. You know, we're going to, all of a sudden, a light bulb will turn on and we'll understand everything. But that's not how you learn. Yes, it will happen a few times in your life. And when that moment comes, you should enjoy it and relish it. But most of your learning and your progress is incremental, step by step. And you learn by small degrees. So, in other words, if you don't have that giant aha moment, it doesn't mean something's wrong. It probably means you're normal. You just keep at it, and after a while, things just get routine and comfortable. And a lot of the math that you had to think about, you know, even like something, say, from last year, you were learning how to take derivatives. A lot of derivatives you just do automatically now without thinking. It comes to you. You have gotten used to it. So just keep at it. You'll get used to it. All right. So our last topic. Well, no surprise. It's optimization. And I say no surprise because I kind of warned you it would be optimization. So what kind of optimization are we talking about? There's 3 flavors. So our first flavor, as we said, suppose we're looking for max and mins, and we had this notion of critical points. And we said, oh, okay, so that's where our gradient is 0. And we had this second partials test. So there's that second partials test. Last time we talked about absolute max and absolute min. And in that setting we said, well, we're going to make a list. And our absolute max and our absolute min has to occur at a point somewhere on our list. And so we just check our list. So the last variation is optimization with constraint. So we're trying to find a max or a min. We'll usually have functions of 2 variables, but you can do functions of more than 2 variables. And we have our constraint. So you'll see, given that x and y satisfy a relationship. Now, sometimes you'll see the phrase given, sometimes you'll see the phrase such that, or where, or satisfying. But the moral is you have 2 functions. One function is what you're trying to make big or small. The other function is a relationship that constrains your choices for x and y. Now, we've done this before. So in Calc 1, we deal with these types of problems. And the way we deal with them is to say, oh, we can use our constraint to solve for one of our variables, and then we can change f of xy to just maybe f of x, or maybe just f of y, and go from there. And that's nice if it's possible, but it's not always possible. So we need to have another method. So that's what we're going to be talking about. Now, the underlying idea about how this is going to work is actually surprisingly easy. A lot of math, when you really dig into it, it's like, oh, that's a simple idea. And here's our simple idea. If we are at our optimum, in other words, we're at a max or we're at a min, we have no incentive to change. We want to stay where we are. That seems pretty obvious. But now let's see what the consequences are. So here I've drawn g of xy equals c. So this is our constraint. So here we have our constraint. And you might say, this looks suspiciously like a level curve. Good. You should think that, because we're going to dig into that in a few minutes. But now suppose I'm at a point. And we'll pick a point. Yeah, it doesn't really matter. Here's our point. And I want to know, is this the ideal point? Well, I want to know how I'm changing. In particular, I want to know how f is changing. So if I want to understand how f is changing at a point, what do I look at? The gradient. Okay, so the gradient of f tells me how f is changing at a point. And let's suppose that my gradient of f goes off in this direction. For just a second, let's suppose that's our case. Now, to help sort of emphasize what's going on, we will pull out our magnifying glass and zoom in. So I'm going to zoom in on this part of the curve. So, zooming in, we have our curve, and we have our point. This is us zoomed in. And we have our gradient. All right, so now the question is, do I want to change or do I want to stay where I am? So, how do I know how to make a decision? Well, I change by moving a little bit along that g of xy equals c. So it's like I'm moving along that level curve. So, how do I know to change or to stay? Well, let's say we call this vector u for just a moment. I look at the directional derivative, that's gradient of f dot u. And if you remember, that's magnitude of gradient of f cosine theta. So, where theta is this angle. the punchline. If theta is an acute angle, if I move in this direction, what do I anticipate? In other words, think about it, is what can you say about the directional derivative? If theta is less than 90, what's the directional derivative moving in this direction? Positive. So if it's positive, if I move a little bit, what's happened to my value for f? It's increased. What if I move in the opposite direction? What's going to happen to my value for f? It's going to decrease. So if I have my gradient and I look at this angle, if it's not, well, okay. If it's an acute angle, I should move. It's an obtuse angle, I should move. When should I not move? Perpendicular. So we're looking for a sweet spot where the gradient of f is perpendicular to that level curve. That's the only time I have no incentive to move. If the gradient of f is not perpendicular, then moving along the level curve, the directional derivative is non-zero, which means changing, I improve. Okay, so that's the big idea. All right. Any questions about our big idea? Okay. Well, we have then the following. If we're at an optimum location, the gradient of f has to be perpendicular to our curve. But we go back and say, you know, there was something about level curves and gradients. Namely that the gradient is also going to be perpendicular to its own level curve. So the gradient of g is perpendicular to the curve. And we want the gradient of f to be perpendicular to our curve. So we say, oh, gradient of f and gradient of g are doing what? They're parallel. They're pointing in the same direction. They're both perpendicular to the level curve. So at the optimum place, that tells me that gradient of f has to be equal to lambda gradient of g. So where lambda, this is a scalar number, and this is called the Lagrange multiplier, named after Lagrange, French mathematician. And so this gives us a constraint. Now here's the important thing, is if you think about our relationships, g of xy equals c, that's telling us a relationship between x and y. It gives us information about x and y. Now what's going to happen is when you have this gradient of f equals lambda gradient of g, this will give us another relationship for x and y. And so what do we have? Well, ultimately what we end up with is we have two relationships for x and y. So you end up with two equations, two unknowns, solve, and life is good. Okay, so here we go. We call this the method of Lagrange multiplier. That lambda is the Lagrange multiplier. So the problem this is for is we're trying to optimize a function f of xy given a constraint. So g of xy is a constant. So step one, we're going to set up a system of equations. Namely that the gradient of f is parallel to the gradient of g. So they're a scalar multiple. And that we satisfy our constraint. Once we have all of that, we say, all right, find all the points that satisfy this system. Now you might think, this feels familiar. And it should. We're going to make a list. So you might say, so the theme for this week is we're like the Make a List Foundation. We're just making lists, right? Well, kind of. but that's the idea. Essentially what's happening is we're figuring out where the interesting points are. Now, when you're solving, you'll notice that there's really three variables now. There's the x, the y, and we've introduced a new thing, lambda. We don't care about lambda, insofar as we don't care about the value for lambda. So we're just going to use it. Now, one of the ways that frequently we do use lambda is we can solve for lambda. So there's a piece of advice which I have found very helpful in solving these systems. When in doubt, solve for lambda. So if you don't know what to do, solve for lambda. Okay, so after you've made your list, now you plug all those points into your function and you interpret the results. But, warning, you have to be careful how you interpret the results. Because there's no built-in mechanism that says, oh, this value is definitely a max or this value is definitely a min. Now there's a couple things that can happen. If your constraint is a closed and bounded curve, then definitely you're going to find the max or the min. But if it's not, things can happen. You might say, hey, can I use the second partials test to tell if it's a max or a min? The answer, no. The second partials test does not help you. So oftentimes when we look at these problems, we'll just say, find the max or min. We won't ask you to verify it because we're not telling you how to do it because it's tricky. Things can happen. But all right, so that's the procedure. Set up our system of equations, find the points, plug it in, life is good. Are you ready to try an example? We'll do it together, right? We'll start. Okay. So, here's one from the fall 2011 final exam. This was my first semester at Iowa State. We had a very interesting final exam. It's a sad story.
Can we hear the story?
Yes. Well, because all the people involved have left. But I had helped craft a beautiful final, and I was very excited for my students to take it. About 4 hours before the final, we discovered that one of the teaching assistants, out of the kindness of their heart, had basically given the students the final to practice. Modulo a few small changes. And we said, well, we can't use that final anymore. So somebody threw together a final at the last minute. So things happened. And one of them is this problem. So it looks pretty innocent. So we're maximizing 1 over x plus 1 over y subject to x plus 4y equals 1. Okay, is this a Lagrange multiplier type problem? Yes, because we're talking about it today. But there's other things that are clues. Namely, there's a function we're trying to optimize. So this is our f of xy equals 1 over x plus 1 over y. And then there's a constraint. So this is our g of xy is x plus 4y equals 1. Okay, so there's an optimization with a constraint, Lagrange multiplier. So we say, okay, great. We have a relationship already. So now we have to find a second relationship. So our second relationship will be gradient of f equals lambda gradient of g. So we're going to dig into that. All right. Well, this says f sub x equals lambda g sub x, and f sub y equals lambda g sub y. Okay, seems pretty harmless. What's the derivative, f with respect to x? Negative 1 over x squared. equals lambda. What's the derivative here with respect to x? 1. Okay. What's the derivative of f with respect to y? Negative 1 over y squared. Equals, what's the derivative of g with respect to y? 4. Okay. Now, we are trying to get a relationship between f and g. So in your mind, as you're doing this step here, you say, look, secretly our goal is a new, this is a big thought, a new relationship for x and y. Right? We need another one. So that's what we're trying to extract from these equations. So I look at this and say, okay, I'm not sure what to do. I have doubts. When I have doubts, what should you do? Solve for lambda. Okay, so lambda in the first equation is negative 1 over x squared. But it's also, from this equation, negative 1 over 4y squared. Okay, well, you can cross multiply. You get 4y squared equals x squared. And we have a relationship now between x and y. Okay, but we can clean that up. What's something we can do here? Take square roots, right? And somebody already said, aha, I anticipate what Steve is going to say. Plus or minus. So remember, if you take a square root, plus or minus. So that leaves us with two cases. So our two cases, we have 2y equals x, 2y equals minus x. We have to explore both cases. But let's start with 2y equals x. We combine that with the relationship we already knew, namely that x plus 4y equals 1. Well, I can replace x by 2y, so this becomes 6y equals 1, or y is equal to 1 over 6. If y equals 1 over 6, what is x? Yeah, 2 over 6, right? Because x is 2y. 2 over 6 also known as 1 over 3. Okay, so here's our point. We made a list of our points. 1/3, 1/6. Okay, 2y equals negative x. Again, we combine that with the relationship we already had. And we say, well, I can replace x by minus 2y. So minus 2y plus 4y equals 1. So what does that tell us about y? 1/2. Okay, if y is a half, what's x? Negative 1. So we have a second point. Negative 1, 1/2. All right, so the idea here is we're making a list of where the maxes and mins could occur. And we've exhausted our all the places where gradient of f equals lambda gradient of g, and the constraint left us with 2 points. Okay, so what's the next thing to do? Plug it in. So we plug it in. So remember, we're taking 1 over x plus 1 over y. 1 over 1/3 is 3. 1 over 6 is 6. 3 plus 6 is 9. 1 over minus 1 is minus 1. 1 over 1/2 is 2. Minus 1 plus 2 is 1. Okay, cool. So, which one's the max? Which one's the min?
We don't know.
Well, what do you think we expected our, because we said find the max, right? So we said maximize. They plug it in. And they said, okay, you got a 9 and a 1. Great. Which one's the max? turns out 9 is a minimum. And 1 is a maximum. And you're probably saying, huh? Because I hear people saying, huh? That doesn't sound right. Well, by the way, we did accept 9 as the answer. But what was happening here? If you sketch x plus 4y equals 1, what you end up with is a curve. It does something like this. But what happens at these points on the curve with our function that we're trying to optimize? It's undefined. It blows up. So actually, as you approach, say, if you're in the first quadrant and you're approaching it, you're getting larger and larger. So you're heading towards infinity and infinity. And in this middle is where that point 9 is. So you're 9, but then you get bigger in both directions. So it's actually a min. On the other hand, this point over here, you're coming from negative infinity up to 1. And then if you keep going in that direction, you're going to go down to 0. So this is a max. So this is why you have to be very careful. Now, this is not to scare you. This is just to say sometimes things happen. And we will just sort of like nod our head, say don't worry about it. And you might say, good thing that never happened again. But it did. A couple years later. Not with the test being leaked out, but there was an optimization problem where it said find the minimum. And in that case, there was nothing blowing up. So I was like, there's no problems. But it turns out there were problems. And the answer, was find the maximum. And the actual answer was infinity, not like 4, which is what they wanted. So you have to think about this. We're giving you points, but if you really want to know if it's a max or a min, ultimately what you have to do is say, just think about what happens if you perturb. What's happening to that point on the curve? Now, that's the level of detail which we put off to your future courses, but I just want to say, be careful. All right, any questions on the basic idea, the philosophy? Set up your equations, get your new relationships, solve for points. Plug in. Yes?
How come you didn't do plus or minus with the y? When you, it's where ways?
Well, once you have one single plus or minus, then you're okay. So essentially, if you have 2 pluses or minuses on both sides, then if you have like plus 2y equals plus x, that's the same as minus 2y equals minus x. So there's redundancy. So you only need to do it on one side. So you pick a side. Yes?
Would you, on like a test, would you assume the biggest numbers in the maximum in most cases?
Yes, you should assume on a test, if it says maximize, whatever the biggest number is, that's the answer. I'm just telling you. Maybe this does more harm than good, but you should know that there's challenges. Okay, well, something more reasonable. Find the point on the ellipse x squared plus 6y squared plus 3xy equals 40 with the greatest x coordinate. Now, good news here. This gets us back into the realm of the kind of problems that we usually ask. So you'll feel more comfortable working through this. Other good news is that we know for sure we're going to get the right answer. None of this ambiguity. Because the function we're asked to maximize is a nice function. So previously we had a function that blew up. Moreover, this is an ellipse. Now, it may not look like an ellipse, but if you covered the 3xy, it looks like an ellipse. What that 3xy is doing is it's tilting. So it's just doing a tilt. So the moral here is because you have this ellipse, it's a closed bounded. Once we have something which is closed bounded, we know there is an absolute max, there is an absolute min. So we know for sure we're going to find it. So if we find something, we have to find the max and the min. Now we might find some points that aren't maxes or mins, but we're not going to be like, oh, I don't know if we found it or not. No, we know. We know. Now we had one relationship, x squared plus 6y squared plus 3xy equals 40. I claim that there's a second relationship we're going to find. What's our second relationship? X equals what? Yes. X equals negative 4y. Okay, so what's going on? Now this is a type on my part, but it doesn't really matter where you put the lambda, which side. So the moral is these have to be multiples of each other. So you might have had lambda times 12y plus 3x equals 0. That would give you lambda equals 0, or 12y plus 3x equals 0. Lambda equals 0 would be impossible because then you get 0 equals 1. So you get x equals minus 4y. Well, if x equals minus 4y, go back to your first relationship. Everywhere you see an x, put in minus 4y. And now you have one equation, one unknown, which you can solve, which says y has to be either plus or minus 2. If y is plus 2, you get x is negative 8. If y is minus 2, you get x equals positive 8. And if you plug those into the function, your largest value is 8. Now, there's a piece here, a tip, pro tip. Make sure your answer is matching what they ask for. So notice, what did they ask for? The point. So what should your answer be? It should be a point. So if your answer is 8, what will happen? You'll lose a point or 2, right? Make sure you know what they're asking for. All right, well, that's okay. We're all warming up. We have another shot. Here we go. Yes?
How come you can switch gradient G and gradient F for which one's next to the lambda? Does it just not matter?
It doesn't matter because they're parallel, so they're multiples.
Okay.
So.
And then also, what happens to our lambda when you make two equations? Because you have 2x plus 3y equals 1 like that.
Right.
12y plus 3x equals 0.
Right. As soon as I saw 12y plus 3x equals 0, that's a relationship, and I'm off to the races. So essentially, my goal here is to get a relationship between x and y.
Only one. You don't need both.
Yeah, sometimes you don't need to use both equations.
Oh, okay.
Yes?
Where did you get lambda times 1 and lambda times 0?
So gradient of f. So here's your f. Derivative of f with respect to x is 1. And the derivative of f with respect to y is 0.
But I don't understand that function. Where does f of x, y equals x?
So when you talk gradient of g equals lambda gradient of f, this is really g sub x equals lambda f sub x, g sub y equals lambda f sub y. It's shorthand notation. So we're saying take the derivative of g with respect to x, set it equal to some multiple of the derivative of f with respect to x. Take the derivative of g with respect to y, set it equal to some multiple of the derivative of f with respect to y. So we're transforming our gradients being parallel into a system of equations, and we want to extract a relationship between x and y. Use that relationship in your constraint. Yes? Maybe back there?
We use implicit differentiation.
No. Implicit differentiation is a different type of problem. So no, there's no implicit differentiation going on at this stage.
I don't understand what the constraint is, like, I guess conceptually. Like, we have that line, y equals x. But what is
Well, this is not the constraint. This is what we're trying to maximize. And our clue is because it says maximize. And so this is our what we want to optimize. How do you recognize a constraint? A constraint literally has a function equals number. So in this case, we have a function of x and y equals a number. So our constraint, this is our g of xy. It's a level curve of a particular thing.
what is that constraint doing to f of x, y equals x?
Well, what it's saying here is if you were to sketch what this is an ellipse that looks something like, it's a tilted ellipse. And it's saying you have all these points on your ellipse. And among all of them, which one is the furthest to the right? So you're exploring the ellipse, looking for the one that's furthest to the right. So it's telling you, I'm not taking arbitrary points. I'm taking points only on the ellipse. Yes? I'm sorry, I can't quite. So what I hope I can. So it sounds like you're asking, how do we use the f? And the. I'm having a hard time hearing, but.
How would we find we got a maximum?
How do we know it's a max?
How do we find x, y, and yeah? How do we,
because it tells us to.
well, if it does, if it's the same property, it didn't give us that.
Well, then they're mean. Now, this comes from an exam. This is an exam question. So this is the type of question they'd ask. So generally, it's something very clear. Like they'll, about the only time they don't give it to you is like distance to the origin. Well, what's the distance to the origin from a point x comma y? It's the square root of x squared plus y squared. And there's your optimization. So, all right, looks like our time is up. So we'll stop here.